In this video, we are going to explore the capability of Foucault Mini-Dyno to maintain constant resistance level for the motor under test, independent of its speed. So first, let's look at the display. Now the set point is 0. Let's change it to something sensible, and I'm going to do it on the controlling PC. So let's set it to 0.02. Okay, so that means that the set point is currently 20 milliNewton meters or 0.02 Newton meters. And now I'm going to start up the motor under test, and let's see how the system will respond. So first, let's just start gradually speeding it up, and you see it responds really fast because it really wants to be where the control is going on. So the system moves the stator where all the action is happening fast, and then it just keeps applying this fine-tuned algorithm. Alright, so we are already at 0.02 Newton meters, so the system has adjusted itself practically almost instantly, and the gap has changed to 1.33 millimeters from the initial gap of 5.00 millimeters. You can see it here. So this is the variable air gap eddy current brake or electromagnetic resistance unit. So this black disc, this black rotating disc, is the rotor with permanent magnets, and obviously another, like that copper colored disc, is actually a copper disc that is providing resistance. Alright, so let's try to gradually change the voltage, maybe down. I'm going to make it move a little bit slower, maybe 237 RPM. And the gap has become expectedly shorter because the slower you go, the closer we need to move. And I'm going to move it a little bit. And you see what is going on here? It is slightly under, but still at 200. Or, in other words, 20 milliNewton meters. Let's go a little bit slower, maybe slightly under 200 RPM. And now, I still can hold it, it still holds. It is very nice. And you can just keep going until I'm going to gradually decrease the speed until we hit the lowest speed at which this kind of resistance can be actually generated. And observe that the gap is really small now. It's only just slightly over half a millimeter, and you can see it here. It is indeed just about half a millimeter. So let's slow it down a little more. And let's see what's going on with the gap. 0.3, and we still achieve 0.2 Newton meter, even though the gap is becoming only 290 micrometers now. And let's just go slower, yet slower. And now I have hit the point where the gap is becoming really small, and the machine can no longer generate 20 milliNewton meters or 0.02 Newton meters. And it got stuck at 0.185, and you see the gap is 0.16 millimeters. The system is designed such that the stator is not allowed to approach the rotor closer than 0.1 millimeter in order to avoid contact. And clearly with this kind of speed of 126 RPM, the next controlling action will push the stator closer than 0.1 millimeter and potentially would result in a mechanical contact, which we obviously don't want. And of course, as a last line of defense, we do have the front end switch, which would actually stop the system before the contact has occurred. However, this is just showing that the system is very robust. It wouldn't do what it can't and only does what it can. Alright, let's now increase the speed substantially while keeping the set point the same, and that will see what is going to happen with the air gap. Let's observe it from this angle, and I'm going to just push the speed up to perhaps 400 or so RPM. So what's happening here? Yeah, and this is the dynamic torque sensor, has a very fast responsive display, and it's already showing 0.0200 newton meters. And the gap has expectably increased to 2.21, 2.22 millimeters. And as long as speed remains unchanged, the system would be sitting at pretty much this gap. However, since over time we are just making not much power, but if the copper will be accumulating heat, will be heating up a little bit, then it would require a little bit shorter distance to generate exactly the same resistance level, so the system would automatically adjust the gap to compensate for temperature increase. So now let's just keep pushing the speed faster and faster, and let's just see how quickly the system can actually adjust. And it is adjusting very quick indeed. We are now at 470 RPM, and we are still at 200 Newton meters, and I can actually keep ramping up the speed while the gap is going to be essentially tracking the increase in speed. And the torque is 200 Newton meters, and we can also observe that same torque on the display of the DIN 200 torque sensor. Let's just get some more sharp image, and let's keep ramping up the speed. And the gap is 3.57. So if we leave it running like this, it would be maintaining it in automatic mode as long as you actually want, and as long as the motor is spinning. What is nice about it, all the control algorithm is running actually inside of this control enclosure. So even if I disconnect the microcontroller from the controlling PC, from the CAN bus, it will still be maintaining the last set point automatically in the fully autonomous mode. Alright, and can we go even faster? I think we can. Yeah, I think this is the maximum I get for this motor, is around 868 RPM. And the gap has become 3.88 millimeters, 3.87. And we are doing again 200 or like 200 hundredths of millimeter or 20 millimeters. Okay, now I'm going to gradually slow down the motor down to 400. And as you can see, when the motor speed changes are relatively smooth, the delay is very small. So essentially the system is tracking the speed almost without a major delay. And let's just do one last test. Let's just change the set point to something slightly different but very specific. For example, 3, 4, 7. And let me just make it a sharper image. There you go, 0.0347. And what's going on here? And we are very close to it, and give it another, yeah, and we are there. So effectively a few seconds, anywhere between 3 and 6 seconds it takes for the system to switch between, say, change its resistance torque to by factor 1.7. We can actually just try to show how it changes by factor, say, 3. Like, really would like to see a large amplitude step input, so we are going to reduce the set point to 116 and 3, 2, 1, go. 1, 2, 3, 4, 5, 6, well, 6 or 7 seconds. So that is a standard response of this control algorithm, and this control algorithm appears to be really robust, and more remarkably, it is scale invariant. We have tested this control algorithm with this very small loading permanent magnet rotor, but of like approximately 50 millimeters in diameter. But we also tested it with 80 millimeters rotors and 110 millimeters rotors, but also 160 millimeters rotors that weigh in the neighborhood of 3 kilograms, really large, and being able to output 20-25 Newton meters. So you can see that this algorithm with really small tweaks, essentially associated with geometrical parameters of the rotors, can equally efficiently and reliably maintain constant torque in the range from 20 or even 2 milliNewton meters all the way to 20-25 Newton meters. And there is no reason to believe that we can't even push it even further up, as well as down to the very small, like 20 millimeters micro size rotors meant for testing really small micro motors, for example, for aviation or for some micro robot actuators. All right. Thank you very much for watching. And if you have any questions, please get in touch with us and to discuss your application.